In this module, we'll look at timber connections and some basic principles that apply to all types of timber connections. We'll look at Type 1 and Type 2 connections, which are the basic categorisation of connections and enable us to design even complex connections using really simple principles. We'll look at joint configurations and how we measure edge-end distances and spacings in connections. And we'll look at some examples of connections at the end. So here's a quite complex timber connection. A connection is required wherever we join members together. And a lot of the creativity in our designs is what we do with the actual connections, how we transfer the loads from one member to the other, and how our work interacts with what the architect requires, whether the architect wants us to express the connection or hide the connection. So, basic categories of timber connections. Type 1 connections simply mean that the fastener has shear on it. So here we have a connection between two pieces of timber, and between them is a bolt. As I put these two members into tension, the load is transferred from one member into the bolt. The bolt then transfers the load across the gap between the two members using shear in the bolt shaft and then into the other member, so that it's shear in the bolt that is transferring the load between the members. If we look at this diagram, we can see at the top left two pieces of timber with a nail between them. As we put tension into both of those pieces of timber, we put shear into that nail. Down the bottom, there are two pieces of timber, but one is perpendicular to the other. As we load with a vertical downward load, we again put shear into the nail. The same types of connections can be made with bolts. And that's the example that I was showing here. And in the bottom one, we can't actually put a bolt on that connection, but we can use a coach screw, which is a large diameter screw that behaves very much like a bolt. In the top right-hand picture, we see a connection between a rafter and a top plate, which makes use of a thin piece of metal. The nails that are driven through the thin piece of metal carry the uplift load out of the rafter into that thin piece of metal using shear. That is also a Type 1 connection. A Type 2 connection is characterised by tension in the fastener, so that it's tension in the fastener that's transferring load from one element into the other. Looking at the left-hand picture, you can see a piece of timber sitting on another one with a nail or a screw between them. As we put uplift on the top piece of timber, we're putting tension into the shaft of the nail or the screw, and that is transferring the load between them. And likewise, in the central picture, we can put tension on the nail or screw by pulling those two pieces of timber apart. In the top right-hand photograph is the same detail we saw before, but the bottom of that metal bracket has a horizontal section, and nails are driven down through that into the top of the top plate. As the whole bracket is lifted off by wind uplift, it's putting tension into those nails. So the nails in that face of the plate are carrying tension. That is a classic Type 2 connection. And it really doesn't matter how complex a connection is. We can always resolve its behaviour into Type 1 or Type 2 connections. Type 2 connections can also be made with bolts or coach screws. Now, for pieces of timber, the most effective connections penetrate the side grain. If we look at this piece of timber here, that is the end grain of the piece of timber, and there's side grain on two faces. So connectors are most effective when they're penetrating the side grain and less effective when they're going into the end grain of the timber. We also want to minimise tension perpendicular to the grain. So if we're loading a member axially, so we're pulling on it this way here, the loads are being applied parallel to the grain. But as soon as I introduce a fastener through that member and then apply loads in this direction, I'm tending to cause splitting across the line of the hole in that member. So we're going to detail our connections to try and minimise tension perpendicular to grain. And finally, We talked earlier about shrinkage, and shrinkage is primarily in this direction or that direction. If we've got two connectors that go into our member, and those two connectors stop the member from shrinking, but the member wants to shrink because its moisture content has reduced, then we're going to find we introduce tensions perpendicular to the grain and have the potential of causing splitting. Conventions relating to edge and end distances. With timber, it's really easy. This is an end and the grain always points towards the end, so that an end distance is always measured parallel to the grain. An edge distance is always measured perpendicular to the grain. And so it is with spacings. If we've got two connectors there, the distance between them is a spacing parallel to the grain. If we've got two connectors like that, the distance between them is a spacing perpendicular to grain. And for all edge distances, end distances and spacings, it is the distance between the centre of the fastener that we're measuring. Now, for some edge distances and end distances, the direction of load is also important, so that if we're applying loads perpendicular to the grain, we may have different requirements for the edge distances, for the end distances, and for the spacings parallel and perpendicular to grain, depending on the direction of the load, so that those spacings may be a function of the direction of the load. In this unit, we're going to be looking at small connectors, nails and screws, and large connectors, bolts and coach screws. They're the only ones that are covered by AS 1720.1. It also has capacities of split rings and shear plates, but these are largely historical, so you'll only get to use those if you have to evaluate the capacity of an existing structure that makes use of those joint types. In order to model the behaviour of the timber, we're using joint strength groups. We classify the timber into joint strength groups, with JD1 being the highest joint strength group and J6 being the weakest strength group. If there's a D in it, it's seasoned. If there's not a D in it, it's unseasoned. Finally, we'll look at some connections. In this connection here, we're making the connection between a beam and a column. Cut into the column is a steel plate. So there's a steel plate in that region highlighted by the red ellipse, and that steel plate is transferring loads from the bolts into the steel and up to the top member. There are other types of connections. This is in a dome, and this connection here, there are lots of these connections at each load point, and they're all hidden. The architect has asked us to come up with some details that are hidden inside the member. These photos in this one were all taken in the same structure. Some of the connections were hidden, some were proudly displayed. Some were very fine connections that had to accommodate some movement. There is some cases where the architect wants us to display the connections. There are other cases where the architect wants us to hide the connections. We can do either. All of them are either type 1 or type 2 connections. So in summary, a range of different types of connections, all categorised as either shear in the fastener, which is type 1 connections, or tension in the fastener, which are type 2 connections. Fasteners are stronger into the side grain. We're going to detail the connection to minimise tension perpendicular to the grain, and part of that is using appropriate spacings and end distances and edge distances on it.